1. The Great Attractor. Imagine you're adrift in the black ocean of space. No sounds, no boundaries, only the endless reach of galaxies, moving, spinning, flowing through the cosmos like leaves in a stream. But something strange is happening. The galaxies are not just drifting, they're being pulled, dragged toward a point we cannot see, a place astronomers have named the Great Attractor. In the 1970s, scientists began mapping the motion of galaxies near our own. What they found was unexpected. These galaxies weren't simply moving away from the center of the Big Bang, as the expansion of the universe predicts. They were also moving sideways, toward a specific region of space. This mysterious flow includes our own Milky Way, the Andromeda Galaxy, and thousands of others, all moving at astonishing speeds, over 600 kilometers per second, toward a common destination. But here's the unsettling part. We can't see where we're going. The region lies behind the dense plain of the Milky Way, in what scientists call the zone of avoidance. Its thick veil of cosmic dust and stars that blocks our view. Still, the movement is undeniable. Galaxies do not lie. Something massive must be there, exerting a gravitational pull on an unimaginable scale. At first, astronomers suspected a dense cluster of galaxies, perhaps even a supercluster, was responsible. Later discoveries hinted at something even larger, the shapely supercluster, over 650 million light-years away, one of the most massive structures in the observable universe. Could that be it? Or is the Great Attractor just a symptom, a ripple caused by something even further beyond? Some cosmologists propose that what we're observing isn't a single structure at all, but rather the combined gravitational influence of many unseen clusters layered across vast distances. A cosmic tug-of-war, distorted by the shape of space-time itself. Others go further, suggesting this pull might originate from something outside the observable universe, a force bleeding in from a multiverse, or evidence of dark matter's mysterious hand at work. And then there's the possibility we're chasing a ghost, that what we call the Great Attractor is an illusion, not a thing, but a gravitational shadow, caused by how matter warps space across hundreds of millions of light-years. Even today, with the most powerful telescopes and infrared sensors, we've never seen the Great Attractor. Not directly, not clearly. It hides in plain sight, shrouded by the galactic curtain, but its influence continues, tugging at galaxy after galaxy in slow cosmic silence. So what is it? A hidden supercluster? A doorway to something greater? A wrinkle in the gravity itself? We may never know, but as we drift through the universe, we are not alone in our motion. We are being drawn, gently, toward something vast and unknowable. And in that mystery lies the wonder of the cosmos, too. Fast radio bursts, a whisper, a blink, a pulse from across the cosmos. Fast radio bursts, FRBs, are some of the most mysterious signals ever detected in the universe. They last just milliseconds, but, in that instant, they release more energy than our sun does in days, and we have no idea what's causing them. The first fast radio burst was discovered in 2007, almost by accident. A researcher, sifting through old data from a radio telescope in Australia, noticed something strange, a burst of radio waves that shouldn't have been there. It was so strong, so sudden, and then it vanished, one pulse, never repeated. Some thought it was a glitch, a data error, but soon others began to find more. Since then, hundreds have been discovered all across the sky. Some come once and disappear, others repeat, again and again, from the exact same place. They come from galaxies billions of light years away, each one traveling across time and space to reach us for just a heartbeat, and then silence. What could create such a powerful, brief signal? The theories flooded in. Some suggested magnetars, extremely magnetic neutron stars. Others pointed to collisions between black holes or supernova explosions. Still others speculated about something more exotic. One repeating FRB, named FRB1 and 21, and has been especially baffling. It was traced to a tiny galaxy over 3 billion light-years away, and it sent out dozens of bursts, not randomly, but in clusters, almost like a rhythm. It's not just energy, it's structure, patterns, intervals, and that's where things get strange, because when a signal repeats, and especially when it follows a pattern, it starts to feel less like nature and more like intention. Some have even suggested, quietly, cautiously, that FRBs could be the signature of advanced technology, alien civilizations using massive energy pulses to communicate across the stars. A form of cosmic Morse code, too fast, too brief, too distant for us to understand. But these ideas are still on the fringe. No clear evidence points to intelligence. And yet, we still don't have a better answer. And theory proposes that FRBs are focused beams, like lasers, produced by alien propulsion systems. Think massive light sails driven by radio pulses, ships drifting on beams of energy. If true, we may be listening not to messages, but to movement. Others think we've only scratched the surface, that what we call FRBs may be many different phenomena, all producing similar signals. A category, not a cause, and the mystery deepens. Some bursts repeat, but only after hundreds of days. Others flicker for seconds, then disappear forever. No two seem exactly the same. And then there are the dark FRBs, bursts that appear without any visible galaxy behind them. Where are they coming from? Are they echoes of cosmic collisions, leftovers from the birth of the universe, or glimpses of something far more complex? To this day, every new FRB detection raises more questions than answers, and as we build better telescopes, we're finding more, not fewer. The universe is full of them, invisible, fast, silent, until suddenly they're not. Somewhere, something is calling, once, then never again, or over and over, like a heartbeat across billions of years, and we are listening. 3. Dark matter. We are surrounded by something we cannot see, something we cannot touch, hear, or measure directly, and yet it holds the universe together. Scientists call it dark matter, but the truth is, we don't really know what it is. What we do know is this: the matter we can see, stars, planets, galaxies, you and me, makes up less than 5% of the universe. The rest is invisible. The rest is The idea of dark matter first emerged in the 1930 CES, when astronomer Fritz Zwicky noticed something strange. Galaxies in distant clusters were moving too fast. According to physics, they should have torn themselves apart, but they didn't. Something unseen was holding them together, something massive. Later, in the 1970 S, astronomer Vera Rubin confirmed it. She measured how fast stars moved within galaxies. The stars at the edges were moving just as fast as those near the center, defying the laws of gravity as we understood them. It was as if each galaxy was wrapped in a halo of invisible mass. That mass is what we now call dark matter, but we still don't know what it's made of. Is it a type of particle, something beyond the standard model of physics? Could it be machos, massive objects like black holes, or WIMPs, weakly interacting particles that pass through normal matter without a trace? We've built massive underground detectors, trying to catch even a single interaction between dark matter and the atoms that make up our world. So far, nothing. Not a blip, not a flash, just silence. And yet, we see dark matter's fingerprints everywhere, in the way galaxies spin, in the cosmic web that strings the universe together, in the background radiation left over from the Big Bang. Dark matter doesn't emit light. It doesn't absorb it. It doesn't reflect it. But it bends space. On galaxies, it shapes the universe, and it may outnumber normal matter 5 to 1. Without it, the universe as we know it couldn't exist. Galaxies wouldn't form, stars wouldn't cluster, life may never have had a chance, and yet it remains hidden. Some scientists have begun to wonder, what if dark matter isn't a substance at all? What if it's a flaw in our understanding of gravity, a sign that Einstein's theories, as brilliant as they were, might be incomplete on cosmic scales? Others propose that dark matter may have its own forces, its own particles, even its own dark atoms. An invisible mirror world living in the same space as ours, separate but gravitationally linked, a universe within the universe. The deeper we look, the more we realize how little we understand. Dark matter is not just a scientific problem. It's a cosmic ghost, a presence we can feel but never hold. And perhaps we're not meant to. Perhaps some truths remain hidden, not because we lack the tools, but because the universe is more mysterious than we dare imagine. We chase shadows across the stars. We build machines to capture what has never been seen. We write equations to fill in the gaps. And still, the dark remains, watching, surrounding, holding everything together. Or the cold spot. There's a scar on the sky, not one you can see with your eyes, but one that lingers in the oldest light in the universe, the cosmic microwave background. A faint afterglow, stretched thin across the cosmos, left behind by the Big Bang. In every direction we look, this radiation is almost uniform, smooth, balanced, but not everywhere. There's one region that's colder, not by much, just a fraction of a degree, but in a universe so finely tuned, even the smallest deviation matters. It's known simply as the cold spot, first detected by the Wilkinson microwave anisotropy probe in 2004, and confirmed later by the Planck satellite. This cold patch spans nearly 1.8 billion light-years across the sky. It shouldn't be there. According to the standard model of cosmology, temperature fluctuations in the early universe should be random and small, ripples that gave birth to galaxies and stars. But this is something else, a massive, inexplicable dip in temperature, a region of space where the universe appears less dense, emptier, colder than it should be. So what is it? One theory suggests it's a supervoid, a giant, underdense region where fewer galaxies exist. If true, light traveling through that emptiness would lose energy, cooling slightly before reaching us. But that explanation doesn't quite hold. The observed temperature drop is too extreme. The void, if it exists, isn't big enough to explain the anomaly entirely. Others speculate it could be a statistical fluke, just an oddity in the cosmic noise. Possible, but unlikely. The chances of a cold spot this large, this pronounced, are incredibly small. So, what else could it be? Some researchers have proposed something far more radical, that the cold spot is a bruise, an imprint from another universe, a collision, not between stars or galaxies, but between entire cosmic realities. In this theory, our universe is just one bubble in a much larger multiverse, and in the early moments after the Big Bang, our bubble may have bumped into another. That impact could have left a mark, a colder, quieter patch in the cosmic fabric, a wound from before time. But such ideas are nearly impossible to prove. The multiverse, if it exists, may lie forever beyond our reach, beyond the limits of observation, beyond the horizon of light. And so, the cold spot remains, silent, chilling, an unresolved whisper in the background of creation. It's not the coldest place in the universe, but perhaps it is the most haunting, because unlike the empty voids between galaxies, this cold comes not from what is missing, but from what might have been. A reminder that the universe is not only vast, but mysterious, and that behind the glow of ancient light, something colder still may wait. 5. Tabby's star. Then it begins to fade. The sun distance, it looks ordinary. From a distance it looks ordinary, faint, quiet, just another pinprick of light in the constellation Cygnus. But then it begins to fade, not slowly like a dying ember, but suddenly, dropping in brightness by 15, 20, even 22%. Then it returns to normal, and then it dims again. This is Tabby's star, officially known as KIC 8,462,852. Is unlike anything astronomers have ever seen. Most stars flicker in predictable ways. If a planet passes in front of them, the light dips slightly, then rises again in a neat, measurable curve. But Tabby's star doesn't follow the rules. Its dips are irregular. Some last days, others weeks. There's no obvious pattern, no orbiting planet, no companion star, no debris disk that we can see. It just flickers. In 2015, a team of astronomers, led by Tabitha Boyajian, published a paper on this bizarre behavior, and the mystery quickly spread beyond scientific circles. People wanted answers. Some suggested swarms of comets, icy bodies breaking apart and scattering in front of the star. Others thought of vast clouds of dust, shaped and shredded by unseen forces. But neither idea fits the data well. The dips are too deep, too sharp, and some of them occur without the expected signatures of dust at all. Then came the more speculative theories. What if, just what if, we were looking at something artificial? What if the star's light was being blocked, not by nature, but by technology? The idea of a Dyson swarm, vast arrays of solar collectors built by an advanced civilization, entered the conversation, not as a conclusion, but as a question. Could Tabby's star be the first evidence of extraterrestrial engineering? Astronomers were cautious, skeptical, and rightfully so. Extraordinary claims require extraordinary evidence, and yet the mystery remains. Years have passed, and we still don't have a clear explanation. More data has ruled out many natural causes, but it hasn't solved the puzzle. We've never seen another star do what Tabby's star does. It stands alone, flickering, fading, reappearing, whispering secrets across 1,470 light-years of space. Maybe the answer is simple, waiting just beyond our understanding. Maybe it's a natural phenomenon we haven't yet discovered, or maybe it's a glimpse of something more, something built, something old. For now, all we can do is watch, observe, wonder, because sometimes the universe doesn't offer answers. It offers mysteries, and Tabby's star is one of the brightest. 6. Rogue planets. They drift through the galaxy alone. No star to orbit, no light to warm them, just endless silence and the pull of gravity faint in the distance. These are rogue planets, worlds without a home, born in chaos or exiled by it. Most planets are tethered to stars. Gravity binds them in delicate orbits, giving rise to day and night, to seasons, to life itself. But rogue planets are different. They wander freely, unanchored, like cosmic ghosts. Scientists believe there may be billions of them in our galaxy alone, perhaps even more than the number of stars. Some were likely cast out, formed in young planetary systems and flung away during violent gravitational shuffles. Others may have formed entirely in isolation, born from collapsing clouds of gas that never gained enough mass to ignite as stars. These silent travelers are nearly impossible to detect. Without a star to backlight their presence, they are invisible to our eyes and most of our instruments. But now and then they betray themselves. As they pass between Earth and a distant star, their gravity bends the light just enough to leave a signature. This technique, known as gravitational microlensing, has revealed their presence. Blips in the darkness, shadows in motion. One rogue planet detected in 2020 was no more massive than Mars. It was the smallest free-floating planet ever discovered. Others are far larger, some the size of Jupiter, with thick, violent atmospheres swirling in permanent night. And then there are the questions. Could a rogue planet harbor life? At first glance it seems impossible. Without sunlight, how could anything survive? But life is stubborn. On Earth, ecosystems thrive around hydrothermal vents on the ocean floor, utterly cut off from sunlight. If a rogue planet had a thick atmosphere, or better yet, an internal heat source like radioactive decay or a molten core, it might retain enough warmth to keep subsurface oceans liquid. Beneath a frozen crust, entire biospheres could exist, hidden from the stars, protected by ice, feeding on chemical energy. These are not the lush Earth-like planets of science fiction. They are cold, dark, and silent. But life, if it exists there, would know no sun. It would evolve in blackness, sensing its world through chemistry and pressure, not light. Even more fascinating, some rogue planets may carry moons. In such systems, tidal forces could generate heat, warming the planet's interior further. A wandering world, dragging a moon behind it, both locked in a gravitational embrace as they drift between the stars. And if intelligent life ever emerged on a rogue planet, what would their sky look like? No sun to rise or set, only distant stars, frozen in place. The concept of a day would be meaningless. Their idea of time, of seasons, of light itself would be alien. Would they even believe in stars, having never seen one? Would they think their planet was the only one to exist, or would they send signals out into the void, searching for light in a universe that gave them none? Rogue planets challenge our assumptions that not all planets belong, and that even in the coldest, loneliest corners of the galaxy, a spark might still burn. One day we may pass one, a dark world, drifting quietly in interstellar space. No light, no warmth, but perhaps something watching, something listening, something that calls the dark its home. 7. The galactic rotation problem. Galaxies spin. That in itself is not strange. The billions of stars within them orbit a central mass, swirling like glowing whirlpools across the cosmos. But the way they spin is where the mystery begins. According to everything we know about gravity, stars near the center of a galaxy, where most of the mass is concentrated, should move faster. But when astronomers measured those speeds, they found something impossible. The stars on the outskirts were moving just as fast as those near the core. In some cases they were moving even faster. It was as if the entire galaxy was spinning like a solid wheel, completely out of step with the laws of physics. This phenomenon is called the galactic rotation problem, and it's one of the biggest unsolved puzzles in modern astronomy. It doesn't happen in just a few galaxies. It happens in nearly every spiral galaxy we've observed. Something is providing the extra gravitational pull needed to keep those fast-moving outer stars from flying off into space. But we don't see it. We don't detect it. It emits no light, no heat, no signal. This invisible mass, inferred only by the movement of stars, became what we now call dark matter. It was one of the first signs that most of the universe is missing, or at least hidden from view. To explain the flat rotation curves, galaxies would need far more mass than what we can observe, often 5 to 10 times more. But where is it? Some believe dark matter is made of exotic particles, things that don't interact with ordinary matter except through gravity. WIMPs, axions, sterile neutrinos. The names change, but the truth remains elusive. Despite decades of searching, we've never directly detected a single particle of dark matter. And yet, the stars keep spinning, defying what we know. Others have proposed that perhaps the fault lies not in matter, but in the law of gravity itself. What if Newton and Einstein's theories don't hold on cosmic scales? Modified theories, like modified Newtonian dynamics, suggest that gravity behaves differently when accelerations are extremely low, like in the outer arms of galaxies. But while MOND can explain galactic rotation curves, it struggles with other observations, like gravitational lensing or the cosmic web's large-scale structure. So we are left in limbo, two competing ideas, a missing substance, or a broken law. Neither fully proven, both still debated. The galactic rotation problem is more than just an anomaly. It's a crack in the foundation of astrophysics, a whisper that we're missing something big, that the universe is deeper and stranger than our equations suggest. Picture a galaxy, its glowing arms unfurling across space, its stars sweeping through the dark like sparks from a spinning wheel. Every star, every cluster, every planet caught in motion, moving to the rhythm of a mystery, a rhythm that has never been fully explained. And perhaps that's the most beautiful part, that even after centuries of watching the sky, the universe still surprises us, still keeps secrets, and in those secrets we find the edge of human knowledge and the beginning of wonder. The wow signal. It came without warning. No build-up, no repeat. Just a single moment, 72 seconds of radio silence broken by something unexpected. In 1977, a researcher named Jerry Eman was scanning the skies using Ohio State University's Big Ear radio telescope. He was searching, as many were at the time, for signs of extraterrestrial life, part of the SETI program, the search for extraterrestrial intelligence. Most nights yielded nothing but static and ordinary cosmic noise. But on August 15th, something strange happened. A powerful radio signal suddenly surged from the constellation Sagittarius. It stood out like a flare in the data, unusually strong, clean, narrow band, and exactly at 1420 MHz. The hydrogen line, a frequency considered by scientists to be a universal marker. It was the kind of frequency an intelligent civilization might choose to broadcast on, precisely because it's naturally significant in astrophysics. The signal was so distinct, so perfect, that Jerry circled it on the printout and scribbled a single word in the margin. Wow. That's how it got its name, the wow signal. For 72 seconds something had spoken, or pulsed, or emitted, and then, just as quickly, it vanished, never to be heard again. The signal's strength followed a perfect curve. It ramped up, peaked, and tapered off, just as you'd expect if a source in space moved across the telescope's field of view. It didn't look like a glitch. It didn't resemble any known satellite or Earth-based interference. And that's what made it so eerie. Scientists combed through data. They checked comets, planets, stars, and even secret military transmissions, but nothing matched. For decades, researchers have searched that same patch of sky, hoping for a repeat. None came. The wow signal was a one-time event. And therein lies the frustration. Without repetition, there's no way to confirm what it was. In science, one data point isn't enough. But it was the right kind of data point, the kind we've long theorized might be the hallmark of intelligent life. Still other explanations were proposed. Perhaps it was a passing comet releasing hydrogen. Perhaps it was a reflection of a signal from Earth, bouncing off space debris. Perhaps it was nothing at all. But none of those ideas fully explain the signal's strength, frequency, or duration. It remains unexplained, and so it lives in a strange space between science and speculation, between noise and message. What if just once something reached out, a distant world, intelligent and curious, sending a beacon across the void, a message in the language of physics, and we caught it by accident and then lost it forever? The wow signal has become a symbol, not of proof, but of possibility, a reminder that the universe is vast, ancient, and full of places we've never seen, that in all that darkness, something else might be watching the stars too, and just maybe trying to be heard. We don't know who or what sent the signal. We don't know if it will ever happen again. But for 72 seconds, the universe whispered something, and for the first time, we might have been listening. 9. Quantum entanglement across space. At the heart of everything, beneath atoms, beneath protons, beneath the building blocks of matter, there lies a world so strange it defies our deepest understanding. It's the quantum world, where particles behave like waves, where probability replaces certainty, and where the rules of classical physics unravel. But among all the strange phenomena in this realm, one stands apart as the most baffling: quantum entanglement. It begins with two particles, phosons, electrons, or others, interacting in just the right way, so that their quantum states become intertwined. After that moment, no matter how far apart they travel, they remain connected. Change the state of one, and the other responds instantly. Not quickly, instantly, even if one particle is on Earth and the other is on the far side of the galaxy. This defies everything we know about space and time. According to Einstein, nothing, not even information, can travel faster than light. So how is this happening? Einstein himself was deeply troubled by entanglement. He called it spooky action at a distance. To him it seemed impossible, a sign that quantum mechanics must be incomplete. Surely, there had to be some hidden variable, some unseen factor we hadn't yet discovered. But over the decades, physicists tested the phenomenon in increasingly rigorous experiments, and the results were clear. Quantum entanglement is real. It's not a glitch in the math. It's not an illusion. It's a fact of the universe. When two particles are entangled, their properties are no longer independent. You measure the spin of one, and you instantly know the spin of the other, even if they're separated by vast distances. It's not that one particle is sending a message to the other. It's that they are no longer truly separate. They are part of a single quantum system, stretched across space. This idea shatters our classical intuition. It challenges the very notion of locality, that things must be influenced by their immediate surroundings. Entanglement suggests that on a fundamental level, the universe doesn't work that way. Everything might be more connected than we realize, and the implications are enormous. Entanglement is not just a theoretical curiosity. It's being used in real-world experiments today. Quantum computers rely on it to perform calculations far beyond the reach of classical machines. Quantum encryption systems use it to transmit information in ways that can't be intercepted without detection, and in the future we may even see quantum networks, entangled systems linking data across the globe in real time. But for all its uses, entanglement remains a mystery. How do two particles remain linked across space? Why does the universe allow this to happen? Some physicists speculate that space and time themselves may be emergent, not fundamental. That entanglement is the deeper layer, the hidden framework from which reality itself is built. Others wonder if entanglement might one day help us explain consciousness, or even the fabric of the cosmos. What if the entire universe is entangled with itself? What if the Big Bang left behind a web of quantum connections, stretching across everything that is? These are the kinds of questions that make scientists nervous and inspired. Because entanglement doesn't just reveal something about particles, it reveals something about the nature of information and how reality stores and transfers it. It blurs the line between here and there, between now and then. And in doing so, it hints at a deeper order, one not governed by force or distance, but by relationship. In the quantum world, things don't simply exist, they exist together. In entanglement, we find a clue, a single thread, leading toward the fabric of the universe. And, though we don't yet understand the full design, we can feel it pulling, connecting, whispering across the stars that nothing is ever truly alone. 10. The fate of the universe. How does it all end? Not just life, not just stars or galaxies, but everything. The universe itself. We know it had a beginning, a single flash of creation, the Big Bang, nearly 14 billion years ago. From that singularity came time, space, matter, everything we know. But what comes after the stars go out, after the last light fades, after the galaxies fall silent? The fate of the universe is one of the deepest, most profound questions we can ask. And the truth is, We're still not sure. For most of human history, the cosmos was thought to be static, eternal, and unchanging. But now we know that the universe is expanding. And not only expanding, but accelerating. Galaxies are rushing away from one another, faster and faster, carried on the fabric of space itself. What's driving this acceleration? Something we call dark energy, a force we don't fully understand, but one that makes up nearly 70% of the universe. Its presence will likely determine how everything ends. One possibility is the heat death, also called the Big Freeze. In this future, dark energy continues to drive expansion forever. Galaxies grow more distant, stars burn out, black holes evaporate, matter decays, and the universe approaches absolute zero, a cold, dark emptiness where nothing moves, nothing changes, and nothing can live. Time stretches on, but nothing remains to mark its passing. Another possibility is the Big Crunch. In this scenario, the expansion eventually slows and reverses. Gravity reasserts itself. Galaxies fall inward. Space contracts. Temperatures rise. And the universe collapses back into a singularity, a mirror of the Big Bang, perhaps followed by another bang, a rebirth, a cycle. But current data suggests this outcome is unlikely. The universe appears too flat, too driven by dark energy for gravity to reclaim it. Then there's the Big Rip, a more terrifying fate. If dark energy becomes stronger over time, its force could eventually overcome everything, not just the pull between galaxies, but between stars, between atoms, between particles themselves. In the final moments, space would tear itself apart. Galaxies, stars, planets, molecules, even the fabric of space-time would unravel. The end would not be cold or quiet, but sudden, violent, and total. And then, nothing. But these are only theories, models built on the limited data we have. Some scientists believe we're only seeing a sliver of the true picture, that other forces, other dimensions, or even parallel universes could shape a future we can't yet imagine. There are also stranger ideas, that the universe is a simulation, and its shutdown will come not through physics, but a command, or that time itself may be cyclical, that endings and beginnings are illusions, and we are trapped in an eternal loop of cosmic memory. But even if we never know for certain, there's beauty in the asking. The universe is not just a place, it's a story, a narrative written in light and gravity and time. We are part of that story, however small. Our atoms were forged in stars. Our thoughts ride on electrical pulses shaped by cosmic dust. We are the universe becoming aware of itself. And so, when we ask how it ends, we are really asking something deeper. What do we mean in the face of it all? What is worth doing if everything fades? And perhaps, in that fading, there is grace. Perhaps the universe doesn't need a grand finale. Perhaps the silence at the end is enough. A stillness full of memory, a darkness filled with light that once was. However it ends, it began with wonder, and as we look forward into that great unknown, it ends with wonder too.